Could you see my slide?
Yes, yes, sir. It is visible.
Yes, okay. Thank you so much. Uh, First of all, I would like to thank Dr. Patel and Dr. Dutta and all the other organizers for the invitation. It is a great pleasure to accept this conference, even with the condition that we cannot meet in person, but it is a great pleasure for me uh, to give my talk online. I would like to thank also the leadership of your university for the warm welcome and for supporting with the conference. So again, thank you all, and thank to the audience. So my talk it is about exponential Diophantine equations involving sequences. So here is my outline. I will make a quick introduction. I will discuss about the motivation of the first result we obtain. I will present the result. I will give a quick sketch of the proof of our first result. And then I will discuss about other results we obtain. And then at the end, I will ask a question about generalized sequences. I will say that this work, it is done jointly with a friend, Professor Florian Luca, and a former student, Chamu Eloge. So let me refresh the memory to maybe people who don't know well some special sequences, like the Fibonacci sequence. The Fibonacci sequence is defined by the initial terms f0 equal to 0, f1 equal to 1, and the recurrence relation fn equal to fn minus 1 plus fn minus 2 for n greater or equal to 2. In fact, there is a characteristic equation related to that, that is s squared minus s minus 1 equal to 0. And we can find easily the roots, alpha and beta given here. And there is what we call a binate formula that can help to find each term of a Visa sequence. And the binate formula, it is the formula we have here. So that is the first sequence I will talk about. The next, it is closely related to Fibonacci numbers, and that is the Lucas sequence. They are defining similarly, except that the initial terms are different, like L0 equal to 2 and L1 equal to 1. Similarly, we can have the binate formula of Lucas numbers given by this expression here with the same roots alpha and beta of the characteristic equation s squared minus 1 and minus s minus 1 equal to 0. The third sequence, I don't know if there is any question, I will be glad to answer. If not, I will continue. I saw a hand, so anyway. The third sequence that I will talk about, it is the Pearl sequence. The Pearl sequence, it is defined by the initial term P0 equal to 0, P1 equal to 1, and Pn plus 2 equal to 2, Pn plus 1 plus Pn for n greater or equal to 0. And similarly, we have the binate formula. Oh, I'm sorry, it is the Pn here. And yes, so alpha here, it is defined by 1 plus square root of 2 and 1 minus square root of 2 for beta. Another sequence I'm going to talk about will be about the rep digit. A rep digit, it is a natural number n. If we give in base g greater or equal to 2, it is a number written into the form. And a is between 1 and g minus 1. In fact, when g equal to 10, we call that simply a rep digit. All these sequences are very well known, and the people are looking for properties related to these sequences. For example, it was a hard problem to find the powers in these sequences. And John Cohn, in 1996, proved that the only solutions of Pn equal to S exponent k greater than 2, it is exactly the only solution are n equal to 0 and 1. So this was the proof. It is using a very simple method, elementary method. And but the question is, if we look at Lucas numbers and we look at Fibonacci numbers, can we use the same method, a simple method, to prove that we have powers in these sequences? So the method was not easy like we can think. So Bujo, Mignot, and 6x proved that in 2006 that if we consider the Lucas numbers, the only powers we can have are 1 and 4. The same result was obtained with Fibonacci numbers. In fact, the method was not easy. They combined two techniques, two main techniques, Baker's method and the modular method. So it was a big, these three results I'm talking about has changed a lot the way we see the study of sequences. So like in 2012, Florian Luca looked at the sum of Fibonacci numbers who can be written at a rep digit. So he considered 3 Fibonacci numbers that can give us rep digit. And he had a finite number, and the numbers are given in the set here. So from there, we decided to look also what will happen with Lucas numbers. So what we have done with Florian and one of my former students, Benedict Normeyo, we look at the sum of 3 Lucas numbers that can give us a rep digit. And we have all the numbers. We continue the same way. And we look also for pair numbers, and we have a result. So, of course, we extended that. Instead of 3, we have 4, and we have done all this type of thing. The reverse of the problem can be done also. Another way, can we have 3 rep digits of the sum of 3 rep digits as a Fibonacci number or pair number or Lucas number? So this was done with one of my former students, Sheffield. And Another thing we thought about is if we can combine Lucas numbers and the Fibonacci numbers, take a sum and have a rep digit, or have a pair and associate the pair and have a rep digit. So, well, the only thing we have done it is we have a look just Fibonacci numbers and two Fibonacci numbers and two Lucas numbers. Okay. Now, about the result I'm going to present here, here is the motivation. If we look at the definition of a Fibonacci number, so we've defined by this recurrence, we can look at that and we can say that it can give us an expression, interesting. The other thing is that we know well this identity. If we take the square of two consecutive Fibonacci numbers, it gives us this Fibonacci number where the index is 2n plus 1. So from there, we look again. If we take n equal to 3, we have also an identity. And from there, we said, can we look at the Diophantine equation, fn exponent x plus fn plus 1 exponent x, ns, plus so on, but we stop at n plus k minus 1, and we take still the power x. And we want to see if the sum here can give us a Fibonacci number. So that is the first project we started with Florian Luca and Eloge Chamu, one of my students. Okay, how we see the solutions. The first identity I looked at a few minutes ago, if we look at the equation, it gives us x equal to 1, because the exponent is 1 here. And we can see that the length here it is 2. And then we have the index it is n plus 2 for m. We look also the second identity I gave you. So we can see that the exponent it is 2, the length it is 2, and the index it is 2n plus 1. And the trivial, the case f3 equal to f1 plus f2, it gives us the solution that we call also trivial solution. So for s equal to 1 and k equal to 1, obviously we have m equal to n. So that gives us the idea about the trivial solutions. And from there, we can, okay, so here is my student. 2 months ago, he graduated, and it is a picture taken during his graduation. I'm here with him. I have my mask. I'm sorry. That is the only picture I have seen in my cell phone. So here is the Florian Luca. As Dr. Patel said, we travel around Africa to help people to understand math, to do research. So we are in October now. Last month, I was in Senegal with Florian Luca, where we went to teach for a week, and we went back to our different places. So here is the Florian Luca here. So he is very well known in the field. And he has so many papers, so many co-authors. And so anyway, the first result we obtain is the following. We say that we prove that beside the trivial solution, the only non-trivial solution we obtain it is the solution obtained by mnkx equal to 6, 3, 1, 3. So how we prove that? So I will give an idea about the proof. So the proof, for the proof, we started looking what we call the Zinckendorf representation. In fact, a number n would have the Zinckendorf representation with Fibonacci numbers if n can be written into V form. So it is a sum of k's Fibonacci numbers with a V condition here. So we look at that and V help us to represent F1 and F2 in Zinckendorf representation. Then we look what we call a primitive dividers theorem, and to look what can be done with the equation that we have. And then we consider, so for we will have 4 steps. The first step it is to consider the small cases. So we consider small numbers and look at what we can do. So using the 2 tools that I mentioned a few minutes ago, the Zinckendorf representation and the prime divider theorem, we able to prove that the only non-trivial solution, it is the solution 6313. So that is for the small cases. So we deal with a k equal to 1 and 2 and s equal to 1 and 2. Then we consider now the highest values, small, not too high, but it is a little above 2. So we consider greater or equal to 3. And we look first some an elementary property about Fibonacci numbers. If we take a Fibonacci number and we know the root that I gave a few minutes ago, so we can prove that a Fibonacci number is between alpha exponent n minus 2 and alpha n minus 1. So this will be important to determine some bound between the parameters of k, n, m, and x. So if the solution, as I said, we give 1, 2, s equal to 1, 2. So we consider k greater or equal to 3 and s greater or equal to 3. We can prove that using the identity that I have here, we can prove that we have m between these quantities. So that is the first thing we have done. So we determine an inequality between the parameter, between m and the other parameters. Then we want to use another tool that is, we want to, in fact, apply Baker's method. And first, we need to define what is called an absolute logarithmic height of an algebraic number. If we consider an algebraic number, so this means that there is a polynomial whose root is alpha. So we can write the polynomial, we can factor the polynomial in this form, where we call the eta I the conjugate of eta. We can define what is called the absolute logarithmic height by 1 over d, the power of the polynomial, log of a0, the leading coefficient, and the sum of the log of the maximum of 1 and the conjugate, the absolute value of the conjugate. This will be very useful to obtain a result that I call the Matveev theorem, but in fact, this is a variant of a Matveev theorem obtained by Bugeaud, Mignot, and Sixek. So what this theorem does, in fact, when you have a linear form in logarithm, The theorem can help you to determine a lower bound of the linear form in logarithm. And then you can use the definition of the linear form in logarithm to obtain an upper bound. And from there, you can combine and obtain a certain inequality. So that is what we have done here. So using Baker's method, we bounded x in terms of n and k, and also m in terms of n and k. And then, in fact, what we have done is that we use the linear form in logarithm. It is a form that can give us a linear form in logarithm. When you take the log of both sides, you have a linear form in logarithm. And we consider the alpha 1 equal to alpha 2 equal to square root of 5, the numbers we have here, and alpha 3 f n plus k minus 1, and the coefficient are m, the exponent we have here. So we use that. Another thing we did, it is to use what we call the reduction method of Baker and Davenport. What this theorem does, the theorem helps us when you combine your things, the parameters, you obtain a bound. Usually the bound is very high. And using this theorem here, the reduction theorem, we can lower the bound that is very high. In fact, here is the Alan Baker. Unfortunately, he died a few years ago. And he had done, he created a method that we call Baker's method today. And that helps us a lot to solve a Diophantine equation. And even first his method, Baker's method, and then the reduction method. And we have all the variant of the reduction method, of course. So after that, the last step, the fourth step is to consider the case where n plus k is small. So what we did is that we consider n plus k between 4 and 140. And we apply the previous lemma to obtain x is less than v the quantity here, and m less than v the quantity. Of course, when you look at these two values, they are very high, 10 exponent 16 and 10 exponent 19. For instance, we don't have any computer to run a program until these numbers. So we have to use the reduction method. So we use the reduction method, and we put the bound of m down to 71,010. And we do the same thing for x. And from there, we can run our computer. We can write a program. We wrote a program in Maple, and we ran that to deal with the small values of n plus k. The next step it is to bound x. So what we have done is we consider, by the way, in the previous step, we consider until n plus k until 140. Now we consider n plus k greater than 140. And we apply again Baker's method and the reduction method, and we obtain the following lemma. So with this step, we put down the bound to 15, the bound of x to 15. And we see that if we consider the powers 15, we can handle that with a computer. So the next step is to bound k now. So we consider x between 3 and 15, and we consider n plus k greater than 141, and we use, again, Baker's method and the reduction method, and we come to the value k less than 13. So again, with a big number, we can handle that with a computer. So the finally computation is done with k between 3 and 13 and s between 3 and 15. And we use the fact one of the lemmas that we have to put a condition that can help us to deal with the values easily. And we see that the t that we set here is between negative 29 and 16, and will help us to run a program quickly and complete the proof of the theorem. So that is at the end of the proof of the main result, the first main result. Then we ask us, okay, can we do the same thing with the Pell sequence? So to remind you, the Pell sequence is defined by that. One known, well-known property is that Pn squared plus Pn plus 1 squared, it is P index 2 n plus 1. And having that, we consider similar equation where we replace Fibonacci numbers by Pell numbers, and we look at the trivial solution like we have done, and we obtain the result. So beside the trivial solution here, we have no other solutions. So that is the second result we obtain. And after that, we consider what is called Padovan sequence. By the way, Padovan sequence is defined by 3 initial terms, A0, A1, A2, equal to 1. And we have a bit recurrence sequence. If you look at the previous sequences I discussed about, we have n plus 2. Here we have n plus 3. So there is a difference in the definition, in the recurrence relation of the Padovan sequence. There is another sequence very close to the Padovan sequence called the Perrin sequence, but we didn't study that. So here are a few terms of the Padovan sequence. So we consider this equation. So another way we replace Fibonacci numbers by Padovan numbers, and we study that. But this time it is a little more complicated. So first, we look at the trivial, the parametric solutions, and we have them, and some sporadic solutions. And what is a little strange is we have more solutions than the previous one. So like here we have seen this type of relationship. Another thing that we have seen it is for a little higher power, we can have some solutions. So we have more solutions than the previous cases. And then we prove also a similar result. So that is the 3 results we obtain. So maybe I'm going fast, but if you have any question, please stop me. Now, for the audience, we have done for Fibonacci numbers, Pell numbers, Padovan numbers, but now they are what we call generalized Fibonacci sequences or sequence. So a generalized Fibonacci sequence is defined for k greater or equal to 2, an integer, we have a the relationship here. So fn k is defined by fn minus 1k, fn minus 2k, until fn minus k exponent k, where the initial terms are from negative k minus 2, negative k minus 3 until 0, all that are 0, and f1k it is 1. So if you look very well with the generalized Fibonacci sequence, we have instead of one parameter, we have 2. Okay. If we look also Lucas numbers, we can generalize also Lucas numbers to obtain what we call K-generalized Lucas sequence. And how they are defined? They are defined similarly like the K-generalized Fibonacci sequence. We have a similar recurrent relationship. We have the initial term equal to 0 until negative 1. So, but for 0, the term 0, we have a 2, and 1, we have a 1. So that is the difference between the K-generalized Fibonacci sequence and the K-generalized Lucas sequence. There is another. It is the K-generalized Pell numbers, and the sequence is defined by this relationship here. The difference is that we have a coefficient 2 here, and the first term we have all zeros until the index 0, and for the index 1 we have 1. So Mike, I will give you some ideas about the generalized Fibonacci, the K-generalized Fibonacci sequence. In fact, if we take k equal to 2, it gives us what we call, we know very well, the Fibonacci sequence. If we take k equal to 3, we obtain what we call the Fibonacci sequence, and so on. So we have all that. So what is the complicated in this here, as I said, instead of having 1, if we take the K-generalized sequence, if instead of having 1 parameter, we have 2. Okay. So we have seen, I would say that these sequences, the new sequences, many people have studied them, like Bravo, Hera, and Luca. They look at the intersection between a Pell generalized, the K-generalized Pell sequence and the K-generalized Fibonacci sequence. And they have obtained other properties or other equations, and they studied that. The other thing that people have studied it is compare with generalized sequences with rep digit and so on. So just to give you an idea about some studies done on the K-generalized sequences. So my question is, could we obtain a similar result with the previous generalized sequence? Another way, can we study this equation here? In fact, it is possible. First, you need to know where to stop. So that is why I put it here, U. If you look at the initial equation, we put k minus 1. So it depends on where you are going to stop. The other thing, and I say that many times, we have two parameters here, n and k. So it is still possible, but it will be more difficult to solve that. So that is the last point of my talk, and I will stop here. Thank you so much. And I'm ready for questions.
Thank you, Professor Togbe. Mr. Mitra?
Introducing myself, I am Assistant Professor from Department of Mathematics, KIIT University. Thank you, Professor Togbe, for a wonderful talk.
Yes, Dr.
Yes.
Yeah, thank you so much.
So far, we have some questions from the participant.
Yes.
That is from P. Kalika. Is there any other generalization form of Lucas sequence which follow trace of Fibonacci sequence?
Maybe if I can have a question online, I will, because there is the background, so I didn't hear where the question. Could you type of a question I can see?
Yes, P. Kalika can talk.
So the audio is not clear. Could you type of a question and I can see? Could you type the question?
Hello.
Yes.
I think I am audible.
Okay.
Yeah, you can continue.
Okay. Thank you, sir, for wonderful talk. Actually, I have a doubt that you mentioned that for generalization of Lucas sequence, you considered a 0, 0, 0, and last two entry is 2 and 1. And
Yes.
based on this, taking a continuous summation, we will get next term. But sir, one thing I have thought that we have studied that trace also follows sequence. Lucas also follow trace property for Fibonacci sequences. If there is a generalized Fibonacci sequence, then if we consider construct a recursive matrix, as usually we know, and if we take their trace, then it will give Lucas sequence of same order. For example, of order 2, Fibonacci sequence are 0, 1, 1, 2, and 3, and so on. And if we take trace of this, then we will get 2, 1, 3, and so on. So there is a property of a trace. So if we generalize this sequence, this concept, then we will get initial value for Lucas is like if we are talking about order k, then first entry will be k, and then 1, and then 3 in this manner. Just I want to say that there is no any zeros in this sequence if you follow trace properties for Lucas.
Okay. Yes. In fact, it is the one generalization. There are many generalization of Lucas sequence. So V, the one we call that the K generalized Lucas and Fibonacci sequence. So there are other generalization in the literature. So I don't know if it is that you are talking about, because it is not just one generalization we have. We have many.
Yes. Thank you, sir.
Do I answer your question?
Yes, sir.
Okay. Because there are some other generalization in the literature. So that is why I mentioned here, we call that the K generalized Fibonacci sequence. Yes.
Yes,
Do you have other questions?
Professor Togbe, I have just one question.
Yes.
In slide 50, you have mentioned that you consider the small case for n plus k is less than 140, I think.
Yes.
it is suppose you just take randomly just 140, or is there any logic behind it?
Oh, yes. Sometimes when you are doing things like that, you try to consider small values. If you take a too high,
Yes.
if you take like a 500, it will give you a big number. And so for the reduction, it will take more time. So that is why you try to find a certain range such that it will be easy when you are going to do the computation.
Okay, so one can take less than 200. It may be correct.
Yes, so you can take less than 140, but it depends how the conclusion can be.
Okay, sir.
Yes, because sometimes if you take too low, you won't have a correct conclusion. You understand that we did for the case 1, 2, and then we consider from 3 to 140. But if you take, you say, okay, I'm going to start from 3, you will have a trouble later. So that is why we cut that in, I will say 3 parts, 1, 2, then from 3 to 140, and then above 140.
Sir, one more question that
Yes.
like generalized Fibonacci sequence, like K generalized Pell sequence is defined. So
Yes.
is it possible to define like K generalized Padovan sequence?
For K generalized for which sequence? Could you repeat it?
Yeah, K generalized Padovan sequence. Like
Padovan, okay. That is possible. I think one of my students told me about a generalization of Padovan and parent sequence, but we didn't study that. He told me about that, and he said he may work on with generalized sequence, but we didn't have any result, for instance.
okay. Thank you.
You are welcome.
Hello.
Yes.
Good evening, Professor Togbe.
Yes. Good evening. Yes, I know.
Sir. Yes, sir. Sir, Professor Vijan was talking about the small case of that n plus k.
Yes.
So whenever we are taking some binary recurrence sequence, so the small case we are considering, I think sometime it depends on the length of the digits. Suppose means the growth of the sequence, means the length of the digits which
Yes.
occur while the numbers grow up. So sometimes I think it depends on that also.
Yes, you may be right, because if you have okay, it is for the result we obtain, we consider binary sequences. So
Yes, sir. If the growth is suppose means growth is exponential, suppose the length of the digits, then if we take some more bound, then it will be much more difficult to compute the means reducing the bounds, I think.
Yes, you're right. Said you're right at a bit level, because that, like what I said for the equation I said, if you want to study that, it may be a little difficult. One thing it is the Binet formula.
Yes, sir.
It is not very clear the way you can handle that. So yes, you use some approximation, so it will be more complicated. So yes.
Okay. Thank you so much, sir.
Oh, you are welcome, and nice to see you.
I am too, sir.
Okay.
Sir, one more question from participant from Ashish, that like Jacob representation for polygonal numbers, we have polygonal number theorem. So can we establish similar results for polygonal numbers? I don't think so. It is. It's
I don't know. I
Okay,
don't
sir.
know. I don't know. I didn't think about that.
Yeah.
So it is, everything is possible if we can find a method to solve that.
Okay.
Yes, everything is possible. But the idea is, can we use our method to do that? I don't know. Yes.
Mr.
So if there is no question, then thank you, Professor Togbe, for an informative talk about the exponential Diophantine equations involving sequences. So I, on behalf of KIIT Dean to be University and the organizing committee of this webinar, extend a hearty thanks to the speaker for spending his valuable time of his busy schedule. I am sure that the participants must have benefited from your talk. So thanks again for the same. Thank you, sir.